So next we're going to look at ways that we can use matrices to model geometric things, transformations of various kinds on the two-dimensional plane. Now, of course, it is possible to use matrices to model transformations in 3 dimensions. We're not going there. That's well beyond the syllabus. We're going to start with the simplest kind of transformation, which is a translation. How do I use a matrix to represent a point being moved from one place to another on the plane? And that's actually fairly intuitive. We're just going to add some amount to the x and the y coordinate. Of course, we might be subtracting if we're going up and left. But that's really all we're going to do. So we're going to take a point or a line or whatever it happens to be, and we're going to translate them by some amount, some transformation, which is just a translation. So this translation would be 1 across and 2 up. Takes A and moves it to A dashed or A prime. Takes B and moves it to B dashed or B prime by adding 1 to the x coordinate and 2 to the y coordinate. So I can represent that with a matrix that's just adding 1, 2. Add 1 to the x, add 2 to the y. More generally, we would write it like this. We take x, y, and we add a, b onto it, add some coordinates, a and b, to get the new position x dashed, y dashed, or x prime, y prime. People say there's different ways. Technically, that's called a prime symbol, x prime, y prime. So let's look at some simple examples. This transformation matrix only has 2 coordinates. It's a column vector. This means it has to be a translation. So we're going to apply this translation to the line segment connecting A and B. So all we do is we'll work out what this translation does, this transformation, which is a translation. What does it do to A? What does it do to B? So that's the general form. You don't have to write that every time. I'm going to take minus 1, 4, my coordinates of A, and I'm going to add my transformation 3, negative 1. Don't get confused, this is 3, negative 1, the translation, not 3, positive 1, which is point B. That's coming next. So A has gone from negative 1, 4 to 2, 3. We added 3, we took away 1. And for B, we went from 3, positive 1 to 6, 0. We added 3, we took away 1. It really is that simple for a translation. Geometrically, graphically, if you prefer, we're taking A and B and we're turning it into A dashed, B dashed. Notice what's happening. I'm going 3 across and 1 down. Each point goes 3 across and 1 down. Suppose I do this to a whole shape. Now, I'm not going to go through all the details. It really is very simple. You just add the transformation to each one. But what's happened here? My translation was 1 across and 3 up. So each of my points and therefore my shape has moved 1 across and 3 up. The question is, what's happened to the area of the shape in this transformation? Well, it should be obvious, but the area hasn't changed because all I've done is move everything the same distance. So for a translation, nothing happens to the area of the shape. And you could prove that if you had to. If, for example, it said evaluate the reasonableness of your answer, you could actually work out the area of each of these parallelograms and find that the total area was the same after the transformation.